So the third problem is more intricate and yeah, it's more involving to solve. So now we are trying to design some sort of a sequence detectors. So what is a sequence detector? So we are given some sort of a sequence. We are given some sort of a pattern, and in the pattern we would like to design. Given an input, we would like to see whether our input is whether our input is matching with that pattern or not. So in your C++ programming course, you would have done the string matching algorithms or pattern matching algorithms. So this is very similar to this. We are now matching the binary sequence of bits. So in a whole string, in a whole number of zeros and ones, we are trying to find out if four consecutive numbers, four consecutive bits are equal to certain pattern or not. So to consider this example, let's say my output yi would be 1 if xi minus 1, xi minus 2, xi minus 3 is equal to 1 1 0 1. So this is my pattern which I want to match, and if it is not matching with this, then output would be 0. So if I want to design this system irrespective of input size, I can again use iterative design. I can think of a design in such a way that whatever is the input size, this particular method will always work. Okay, so now we are trying to design this sequence detector using this example, but again I would say that it doesn't matter, it does not depend on whether this pattern is this method of designing sequence detector is generic enough, and it can work for any kind of patterns, any kind of bits pattern, I would say. So if this problem is given to us that I would like to match a particular pattern in a sequence of bits, how should I go about it? So to understand how we should go about it, the first thing we have to do is we have to first maybe take an example and see how does it actually work. So now these are the 12 bits of input, and now if I want to see the output, see this particular bit is the LSB, so that means this is x0, this is x1, this is x2, x3. So for x3 to 1 0, it doesn't match, so that means my output would be 0 for all of these cases. Similarly, output would be 0 for this y4 also, because this pattern doesn't match. y5 also 1 0 1 0, it doesn't match, so it would be 0. So but for y6 it is 1 1 0 1, so y6 is 1. y7 is again 0 because this pattern 0 1 1 0 does not match, and y8 is also 1 0 1 1, so it's also not matching, so output is 0. But for y9 1 1 0 1, it is the pattern is matching, so the output is 1. And for y10 and y11 also it is not matching, so the output is 0. So essentially we are taking some example to see that how it work out and how the output would be 1. Now if I want to design this, how should I go about it? So basically I have to create a cell. And if I somehow able to identify that how many bits has matched the pattern already. Okay, so if the input to this cell is how many bits of pattern has matched already, then considering the current input, then we can say that including this particular current input, how many bits have matched, that would be the output. So if we have such kind of a generic input and output, then we can have this iterative cell starting from bit 0, bit 1, bit 2, bit 3, and this can go on for n number of bits. Okay, so that means somehow we have to create this information and we have to process this information, that what is the how many bits has already matched. So now there could be possibility that number of bits has not matched, none of the bits has matched, or 1 bit has matched, or 2 bit has matched, or 3 bit has matched. Now there is also possibility that all the 4 bits has matched, but all the 4 bits has matched. This particular possibility we can remove, because we can always see that for 4th bit to match, so we can have this y output as 1. But this particular information that how many bits has already matched, we can reuse. We can use only this first no bit has matched, first bit has matched, 2 bit and 3 bits has matched. So you can keep information only till that level. So if I have these 4 pieces of information which need to be stored or which need to be remembered, that if either none of the bit has matched, 1 bit has matched, 2 bit has matched, or 3 bit has matched, so how many bits I would require to represent this information? Since total number of information is 4, the total number of bits I need to keep to remember this information would be 2 bits. So let me call these 2 bits as Ci, and I can now say, so this is called encoding. So this encoding could be independent of whatever we say, but let's keep it simple. So we say that Ci is 2-bit input as well as 2-bit output also. So if Ci is 0 0, we say that no bit has matched till now, and if Ci is 0 1, we say only 1 bit has matched, and if Ci is 1 0, then we say 2 bits has matched till now, and Ci equal to 1 1 means 3 bits has matched till now. So I'll repeat this particular question again, that why we are not keeping another information that all the 4 bits has matched till now. Since this is an iterative design, and the input to this iterative cell would be given as a output to this iterative cell would be given as an input to the other one. So this particular information that all the 4 bits has matched is of no value to the input circuit. So input circuit, I just want to understand whether one of the previous bits or whether 2 bits of the pattern has matched or 3 bits of the pattern has matched. So here we can also say generically that if my pattern will have n bits, I have a n bit pattern to be matched, then this value of Ci would be, or the number of bits in Ci would be equal to log n of the base 2. Okay, so which particular pattern, which particular information should I call 0 0, which particular information should I call 0 1 1 0 and 1 1? This is actually independent. It doesn't matter. For design, it doesn't matter. For optimization, yes, there could be sometime advantage over one or another, but as a design exercise, it is more scalable that we keep in a order 0 0 0 1 1 1 1 0, so that it's simple to write, and after that for analysis also. Okay, so what is the next step? So here till now we have understood that this is the information to be copied. The overall design of the pattern would be something like this, that so this is the single slice or single bit design of my sequence detector SD. So here Ci is the input. Ci is a 2-bit wide input, and every time we are checking for Xi, and the output is Ci plus 1, which is also 2-bit. Okay, so the output is yi. So now if I want to cascade, so it will start from 0. So basically it will start from right towards the left. That was the pattern anyway in the sequence detector, that yi equal to 1 when xi minus 1, xi minus 2, xi minus 3 is equal to 1 0 1 1 1 1 0 1 1 0 1. So what is the next step? Now we have found out the slice, we have found out what is the input, what is the output, how many bits in the input, how many bits in the output, and So what is the next step now? It would be better that we write a truth table. So after writing the truth table, then we can find out how we can determine the output. So I am writing the truth table at once, but we'll try to understand it in a row by row. So let us consider that input is no bits has already matched. Because no bits has already matched, and if my xi is 0, then again I have to say that no bit has already matched. But if no bit has already matched and current input is 1, so then I have to say that at least one bit has matched. Because one bit has matched, the output will become 0 1. Now in case of 0 1 input, so that means one bit has already matched. Now the current input is 0. If current input is 0, so that means now 0 1, these two bits have already matched. Okay, so the output will become 1 0, output still remains 0. Similarly, if the current status is 0 1, that means only one bit has matched, and again xi is 1, so that means it become 1 1. So 1 1 is of no use, so that means we again say that only single bit has matched. So the output will also be 0 1. Ci plus 1 is equal to 0 1, and the yi would be 0. Now in the second state where we say that 2 bits has matched, 2 bit means 0 1 is already there. Now the third bit is 1 or third bit is 0. If third bit is 0, then everything has gone away, so we will say that no bit has matched. The pattern does not match with the existing pattern, so it becomes 0 0 0 1. 0 0 1 does not have any meaning here, so we will say that none of the bit has matched. But if the current status says that 2 bits has matched and the next input is 1, so then we have to say 3 bits have already matched. So that means we'll write in Ci plus 1 as 1 1, so that means 3 bits in the pattern has already matched, output is still 0. Now if 3 bits has already matched and the current input is 0, so that means it become 0 1 0 1. 0 1 0 1 is we can say it's of no use, but we can still say that 2 bits has already matched. There we can utilize that, and so the state will become the second state, which means 2 bits have already matched. Now if 3 bits were already matching, the current input become 1, that means the output will be 1, and the next state, the next carry output would be only single bit has matched, so 1 1 0 1. So in a long sequence, if we see that, we can say that only one input as matched in the pattern, so 0 1 would be the output here for Ci plus 1. So in this way we have to see carefully for each and every input pattern, and we see where we have formed, what we have created so far, whether that particular pattern has matched how many bits of the current pattern. Okay, so once we have this truth table, now we know what to do. We can write 3 K maps, one for 0th bit of Ci plus 1, another for first bit of Ci plus 1, another for yi. So if I write all these Boolean equations, I'll create using my truth table. Then I'll have some equation something like this, which says that 0th bit of Ci plus 1 would be determined with this equation, first bit of I plus 1 would be determined by xi, and yi would be determined by these three. Basically all of these condition has to match. Basically this has to be 1, this has to be 1, this has to be 1, then the output would be 1. Okay, so this sequence detector is a very interesting application and which can be used, but yes, you may feel that we have not done enough. So if some more examples would have been taken, then it would be even better. But I'll tell you or promise that in one of the next weeks we will do couple of more exercises, but then the sequence detector would be designed using some alternative technique which are applicable here also, but there we'll use, instead of iterative design, we'll use sequential design. So in the sequential design, some of the techniques can be applicable. We can apply those thinking, those thoughts at least, in designing it using a combinational circuit as well. Okay, so with this I would like to close this particular lecture, and with couple of more applications which you can try yourself. You can take it as a tutorial of this particular lecture. So let's say if I want to do sum of an array x can have a number of elements. So here also, if we do an iterative design, we create an adder, and that adder will give the output to the next adder. So this way, this also could be an iterative design and can be used effectively to find out the sum of an array x. So let's say similarly, if I want to know the dot product of two arrays x and y, so that means I need to multiply each element of x with the corresponding element of y and as well as add them. So then also we can use such an iterative design where where both of them would be multiplied as well as added, and the added output would again be given as an input to the next stage. So in each stage I'll have three inputs, one as the addition or accumulated addition from the previous stage, as well as xi and yi, and there would be one output that would be again accumulated additions so far. Okay, sometimes we see that all these techniques of iterative design may not be very effective. So for example, we have seen in ripple carry adder that ripple, instead of a ripple carry adder, is slow because we are iterating through all these stages and carry is rippling through all these stages, and then we get the output. But the other design like carry look ahead adder or carry skip adder, they're more efficient. Okay, taken, yes, this could be the possibility, but this iterative design offers still more advantage, some advantage in terms of simplicity and repetitiveness. So design would be simple, design could be designed very fast, because when you're designing a cell, then you're designing only one cell, you can verify it more efficiently, and then reusing will cause less of the verification effort as well. Okay, so we can summarize this particular lecture as that this a very simplistic but powerful way of designing circuits. But but given a problem, let's say some problem is given to you, whether first you have to identify whether that problem can be solved using iterative design or not. So that decision can be made quickly by focusing on the overall problem. If problem looks that it could be solved in a similar fashion for all the bits, then we can use iterative design. And once we have decided that we are going to use iterative design, then focus on one cell, and for one cell try to identify what would be the inputs, what would be the outputs, and what is the meaning of that particular input. That is more important. So once we know the input and output, we know their semantic behavior. So for example, in our today's lecture, we our sequence detector, the sequence detector has input ci and ci plus 1. So the semantic of ci and ci plus 1 we have identified ourselves. We said that ci will be 2-bit, ci plus 1 will also be 2-bit, and this is the meaning of 0 0 0 1 1 0 and 1 1 in case of sequence detector. So that way we have to decide what are the inputs, output, what is the semantic meaning of input and output. Once we know input and output, then we can go ahead and create truth table, or sometimes Boolean equations are fast, then we can use Boolean equations also, and after that our design is almost ready. Okay, so this is also the last lecture of this particular module. So I'll also summarize this overall module in couple of minutes. So in this particular module, the objective was to design a boolean combinational logic or a boolean system, so or a digital system using basic gates. Now the question which we the question with which we started this module, that how to write boolean equations given a problem statement. So during this whole module, last 8 lectures, we have seen different scenarios, different cases, and in most of them we have focused on how to write, how to give these boolean equations, how to give input specification. So the overall observation is that these Boolean equations are essentially synonymous to the behavior or the functionality of the design. So if functionality of the design is clear to us, behavior of the design is clear to us, in most of the cases Boolean equations were formed automatically by using by using our rational and by using our logic. Okay, so using those Boolean equations, then we have also formulated, we have also seen couple of combinational circuits which are very commonly used in different applications like multiplexer, demultiplexer, encoder, decoder. So there were various circuits that has been discussed, and along with using understanding these commonly used combinational circuits, we have also seen design of arithmetic circuits, adder, multiplier, comparator, and we have also seen how to design them more efficiently. So this adder as well as multiplier both offer some sort of a parallelism. A sequential process is usually slow, so we have found different techniques of doing things in parallel so that multiplication could be faster or addition could be faster. We have also seen there is a area and delay trade-off. So if we try to optimize the delay, then area would usually increase, while the simplistic technique or the naive technique will have lesser area, but the delay is usually more. And in today's lecture we have seen iterative circuits, which is also an interesting approach or a different approach to design any particular circuit. So as a end goal of this particular module, we should be able to attempt a digital design problem with a combinational logic. So if a problem is given to us, then and we have to solve, we have to design that particular behavior or that particular function. Then first we need to break that function into smaller pieces, and we need to see that can each and individual part of these individual parts or small pieces, can they be implemented using anything which we have learned so far. So for example, multiplexer, demultiplexer, adder, multiplier. So it could be quite possible that we may not be able to design directly using them, but during this whole module we have not only learned how multiplexer is working, but we have also learned how to design a multiplexer. We have not only learned how a demultiplexer can be used, but we have also seen how to design a demultiplexer or a decoder or an encoder. So given a requirement, given that particular module, we have identified that let's say multiplexer need to be used, then but the same multiplexer cannot be used because let's say number of inputs are not 2 to the power n. Then we may modify or we may redesign that multiplexer, demultiplexer, or we can have a unique kind of an adder. So because the whole module has not only focus on application oriented part, that we can use only these cells, but we can also design. So given a problem statement, first we can think of that how we can break things into different parts, then each part which particular kind of design can be useful, and if nothing works out, then we may have to go for a custom solution for that particular problem. That is also fine, but with all these techniques in your arsenal, then you can find out how to design a new concept or a new system which has a different functionality. Okay, so with this particular end of module, I believe that you should be able to design different kind of a combinational logic with whatever techniques we have learned so far. Thank you very much.